Hello everyone, welcome to another CCOM-JHC seminar. Our speaker this week is my advisor, Tom Lippmann. He's an oceanographer in the Department of Earth Sciences, and he works here at the Center for Coastal and Ocean Mapping. I'm sure almost everyone knows him. He's also the director of the Oceanography Graduate Program, which is increasingly important to a lot of us, it seems. He works with Ocean Engineering Graduate Program and the School of Marine Science and Ocean Engineering. All his research is generally focused on shallow water oceanography, hydrography, and bathymetric evolution in coastal waters, spanning the intercontinental shelf, surf zone, and inlet environments. He does all his research using a combination of experimental, theoretical, and numerical approaches. And over his years of research, he spent 3 years in the field, so he's very knowledgeable in field work. So here's Tom. Sure.
Okay, yeah, thank you all for coming. Appreciate that. One thing I would like to emphasize is that at UNH I have a large number of affiliations. I work with a lot of different groups, and in particular many of those groups intersect right here where we are right now. This is where my lab is. This is where a lot of my students are, and anyway, it's a very good place for me to be over the years. I've been at several institutions and I have a lot of resources here, which I both had and did not have at other places. It's a pleasure to work with all of you over the years. I'm very happy about it. Thank you for all the help. In a minute, I'll talk about some acknowledgments of people who helped me specifically with this work. But what I want to talk about today primarily is subtidal currents. When I talk about subtidal currents, I'll also be talking about tidal currents as well. It's hard to sort of separate the two and to sort of discuss a little bit about tidal fluctuations. And I'm particularly interested in currents and water levels in shallow water. Not so much in the open ocean, but what happens to currents and water levels in shallow water. And I'll touch briefly upon why that's important. Not a big part of the talk, but nonetheless, I want to mention a few things. So this talk I'm going to break up into two different components. One will have to do with currents, and the other will have to do with water levels. Currents will be measured with ADCPs. We'll talk a little bit more about this in a minute, and I'll focus on the new River Inlet experiment, which took place in 2012 in North Carolina. And as part of that, we'll do a tidal analysis to remove tides, and then we'll filter that data with a low-pass filter, a nice time domain filter, to estimate what the low frequency subtidal fluctuations in the currents are. We'll do that with both currents, and we'll also do that with pressures. We'll look at the subtidal currents and their relationship to the wind fields, both inshore and offshore, and also look at the long-term average flow fields in New River Inlet. For the water levels, I'm now going to use a bunch of data that's been collected in and around this area, in the Piscataqua in 2007, in the Great Bay in 2010, and in Hampton Inlet in both 2005 and again in 2011. Okay, so what I want to mention first are thanking the people who have participated in these experiments. I've been involved in the first two that I list up here. That's the Hampton 2011 and the 2012 New River experiments. A significant number of people from the center basically helped me with this. In particular in Hampton, this is part of Lindsay McKenna's thesis. She was participating in the other experiment as well. But Jim Irish has been a major component of these experiments, particularly in the observations of the currents. And of course, John has been working with us in helping deploy these things. In the previous experiments, I was here for 2010, but not really actively involved in that experiment. This is data that's been collected by people at the center here itself. Jim Irish and Larry Ward, in particular, for the Hampton Harbor 2005 experiment. And we'll talk about some of the data collected there. The Piscataqua River ADCP surveys or deployments by Carl Kammerer, funded by NOS. And then the Great Bay data collected by Jim Irish as part of Sean Denny's thesis research. So I want to thank everybody who participated in those and just make sure that they get the credit where it's due. I want to make one final comment about Jim, because Jim and I have been working significantly closely together on this data. What I usually do is I come to him with some questions. I'm seeing this weird stuff in the data. What do you think of that? And he says, well, I was just looking at some data from these other experiments, and then he hands that off to me and we start working and sort of discussing that. So much of what I talk about today will have been discussed with Jim, and we're writing papers together on these topics. Okay, so I want to make a few words about currents and water levels in shallow water and the reasons why, for us, they're important. And these are just a few of the things that I want to touch upon. There's others, I'm sure. And in particular, from an oceanographic standpoint, there's transport and mixing that go on in shallow water that are strongly dependent on currents in particular, but also on water levels, both directly and indirectly. And this is heat, sediment, and nutrient transports. There's exchange between the shelf, the nearshore, and estuarine systems that are very important for productivity reasons and also for biohazards, algal blooms, and so forth, primarily related to the type of nutrient systems that are in the region. Navigation, of course, which everybody here is pretty much familiar with, both for shipping and small boating. This is for mariners in general. They need to know water levels, of course, for safe navigation, but also currents are extremely important. So we map currents and that kind of thing for small boating safety. And these problems are exacerbated by sediment transport in shallow water, both erosion and depositional regions. So from a navigational perspective, currents and water levels and hydrodynamics associated with those become very important. Interactions with structures and engineering as forces on bridge piling, scour, deposition, and dredging, of course. Storms where you have inundation and flooding, particularly from wave-driven currents and setup. Secondary processes is driven in very shallow water. And then finally, of course, for ocean mapping, both operationally and when you need to know how frequently you need to measure the bottom because it's changing both in time and space. We not only want to measure it, we want to understand it well enough to be able to use it. Okay, so these are sort of some of the reasons why we focus our energy on shallow water, particularly why I'm there. Okay, so let's get to talking about the New River Field experiment. This is New River Inlet. This is in North Carolina. This is a Google Earth image of the inlet itself. This is funded primarily by the Office of Naval Research as a marine base just to the north of the inlet, which is one of the reasons why we were there. But this picture gives a nice picture of a very narrow, about 700 meter wide mouth opening to the inlet itself, very shallow. I'll show you a closer picture in a minute. As shallow as 1 meter at low tide. And a very narrow, 10 meter long channel heading up into the inlet, which opens into a very large back bay system. And also connects strongly to the intercoastal waterway, which propagates to the north and to the south, which have openings to other inlets in the nearby area. So it's complicated in the back bay, but one thing we do know is that the amplitudes of the tides that propagate into the inlet are very strongly attenuated. And about 90% of the energy is dissipated by the time they get into the deep back bays, which means that these waves that propagate as tides into the inlet are not standing against the shoreline. They're actually progressive waves that decay in amplitude. So what we see at the mouth of the inlet is not a standing wave pattern, but a progressive wave. That is to say, the orbital velocities associated with the tidal motion is what gives us the incoming and outgoing flows. And the phases of the tides are 90-degree different than what you normally have. Slack tide does not occur at high tide. It occurs actually at mid-tide. The strongest currents are at high tide. In any case, the tidally choked nature of this inlet separates it from some of the other inlets we've looked at. We're going to focus our energy on looking at what's going on right here at the mouth. And this is a bathymetric map of the region showing the inlet opening and the location of our ADCP. So the scale over here is relative to mean sea level, or I guess NAV-D80, which is very close to mean sea level. There's about a 10 meter deep channel in the main portion of the inlet, but the opening across the ebb tidal show is very shallow. And it's about 1 meter actually at the opening, so there's a significant amount of wave breaking that goes on the ebb tidal show itself. There's two inlet channels. One's really kind of a remnant old channel, but it is still has a significant amount of flow associated with it. As part of this experiment, we deployed an ADCP offshore in about 9 meters water depth, another one inshore in the heart of the main channel in about 8 meters water depth, and another one on the flank of the inlet channel at the northwest corner of the inlet channel. Note that the currents here at this particular location heading up into the inlet are basically going north-south, and the inlet and the orientation of the shoreline is roughly heading out northeast to southwest. Okay, we also have observations of atmospheric properties, including wind, at both these two stations. We'll talk about wind data from this particular sensor located here. Okay, the data itself was collected with acoustic Doppler current profilers. This is a picture of Jim's ADCP. This is a 600 kilohertz. This is in the frame that was deployed offshore. There's battery packs, enough to make it last longer than 4 weeks. And we recovered it with a acoustic release with a pop-up buoy, which for some of us, including John, you have to go down and bump it with your head to make the buoy come up actually. But we got it back, which is very good. In any case, the ADCP measures currents in 3 dimensions, that's UVW components, as a function of depth above the transducer or distance above the bottom. So in a whole profile ranging about 1.5 meters off the bottom to the surface, we're getting velocity estimates every second. They're very noisy, so we average them in time. And the data I'll be showing are averaged over 30-minute intervals. They also have pressure sensors in the transducer itself, so we can measure surface fluctuations as well. We deploy them like this, and then we sit and wait for a while and hope that we can go back and get them. When they come back, this is the other frame that went in. They look like this. There's a significant amount of biofouling and growth. When Jim's not there, we try not to let him know about this. We clean them up, and then we send them back to him. But one thing I want to point out is that the ADCPs are nice because they rely on the Doppler shift of the current. That is, the particles that are moving send a Doppler shift to the acoustic signal back to the transducer itself. That's not impacted by the biofouling. There's some attenuation, but it's very weak. But in terms of the Doppler shift, there's no change in the current. So the reliability of the sensors are quite well over time, even if you're in warm areas like this where you have significant biofouling. Okay, so quickly, I want to talk about the conditions during the experiment in New River. There's several panels here. These are all time series over about a 4-week period from late April to late May. The tides are shown in the upper panel, spring tides occurring, semidiurnal spring tides in the center or middle part of the experiment, ranging from 1 to 2 meters throughout the experiment. A couple things to point out are that the waves generally propagated out of the south or southeast. That's sort of this panel right here. And they were strongly tidally modulated at the mouth of the inlet because of the changes in the tide level itself. When the tides are low, the waves tend to break on the bars offshore, particularly the high frequency sea waves. The swells tend to propagate into the inlet itself. And so we see that in the sensors on the north and south side of the inlet itself. There's more wave action at high tide on the northwest side of the inlet. There's very little wave action on the southern side because of refraction over the channel and so forth. In any case, there is wave and wave-driven currents inside the inlet that's tidally modulated but also driven by wind processes on the shelf itself. These two panels right here basically show the magnitude and direction from which the wind is coming from. And the magnitude of the winds change from about 5 to 10 meters per second typically throughout the experiment. That's 10 to 20 knots. And they tend to vary significantly from all different directions. We had many passages of several fronts throughout the experiments. The depth average currents from the ADCPs are shown down here. The green is from the deep channel, has the largest magnitudes. They're also semidiurnally tidally modulated. And then the black line is from the northern part of the inlet. The currents are a little less strong there. And then offshore, they're significantly weaker out on the shelf itself. The directions from which the currents are going, or towards the direction from which the currents are going, are shown here, showing the tidal modulation within the inlet itself, very strongly collimated by the bathymetric contours, both to the north and south of the inlet itself. Inside the inlet, that's the green and the red lines. So we see the flood tides and the ebb tides alternating, incidentally, very rapidly. The turnover of the current was not really a transition, it was an event.
What would be the currents or subtidal currents?
We'll get to that in a minute, but we're going to remove the tidal fluctuations and then look at the low frequency oscillations associated with longer period. And in fact, in this case, related to the weather forcing.
Does sub mean below then? Or?
Below in frequency. So below in frequency. And I'll talk a little bit about that when we talk about the filter. And you can see at times when offshore, the range over which the currents are changing is very narrow. That is, the phases over which the currents change is not 180 or 360 degrees. That is, it's not going around in an ellipse. It's being pushed to one side based on the wind patterns. And we talked a little bit about this when we looked at Lindsay's data earlier at Hampton. And there was a clear relationship between the direction that the winds were blowing and over the directions over which the tides would actually move. So the tidal currents are actually modified by the directions of the wind based on the wind-driven flows in that area. And that's why we see this narrow change in the offshore currents, and they tend to move around in different ways. Okay, so this is the thing that first led us to start thinking about what's modifying the currents based on these wind patterns. Okay, so let's get back to New River here and talk about some of the data now. So here is the offshore ADCP. We'll look at this first, and then we'll look at some of the inshore ADCP data. So now let's look at the currents over the 4-week period. So again, time series over 4 weeks. The vertical axis is depth above the bottom. So 0 is at the bottom, And you can see where the surface is up here, where the tides are actually moving back and forth. This is in about 8 to 8.5 meters of water depth. This is the magnitudes in the upper panels with the scale on the right, ranging up to about 80 centimeters per second. And this is the direction towards which the currents are going, also from a 360-degree range. So what you see clearly there are fluctuations in the currents offshore that are due to tidal modulations. You can see the tidal fluctuations in the variability, but you can also see longer period fluctuations associated with these subtidal motions that we want to look at. You can also see changes in the directions of the current, which are clearly modulated by the tide, which are more strongly modulated by these lower frequency episodic events associated with weather forcing in the area. We've spent a significant amount of time looking at the vertical structure of the tidal motions themselves. That is to say, we wanted to specifically look at the tidal frequencies and see how they varied with depth, how they rotated in response to the boundary layer, and how the phases and coherences changed. And we've written a paper on that. And this is a continuation of work that I was doing in much shallower water. Nonetheless, we have looked significantly at the tidal motions. Now we want to remove those tidal motions and look at some of these longer period weather forced fluctuations. We can look at this in a little more detail, and I'll just look at a week's period in the middle of the experiment here, so you can see some of the variations that occur through time as a function of depth. And you can see things that happen where you get rotations in particular directions that go in one direction in one place and in another direction in the other. So we're seeing currents that are rotating clockwise and currents that are rotating counterclockwise, and this rotation can change over the vertical, that you can have currents that are doing oppositely rotating kinds of things. It's very complex. Okay, so to get rid of tidal motions, we need to do a tidal analysis of this data. And we're going to do this by taking time series at each of the different locations. And we're going to run the tidal analysis and then remove the tides from that data. And we can do this using this T-tide program developed by Rich Palowitz. See, Woods Hole, right? Jim?
Yeah.
Rich, yeah, from Woods Hole.
Really Mike Foreman's squares fitting.
Yeah, so it's a regression analysis based on the tidal constituents that we know. We can do this because we understand very well what the tidal forcing is. So what we have here are raw spectra as a function of frequency on a log plot. These are raw spectrum with 2 degrees of freedom. The green is the filtered data after we've done the tidal analysis. So the blue line indicates the pre-filtered data. So you see the tides at the diurnal and semi-diurnal and so forth, the other periods. So we can remove those tides very well. This actually is from the pressure data. So this is showing the elevations, and us removing the data of the pressures from that. You can also remove this from the currents. These are the north-south velocity vectors, and these are the east-west at one particular elevation. So once again, we can remove those tidal constituents. One thing to note, though, when you look at these specters, there's significant energy at low frequencies and subtidal frequencies from the semi-diurnal tides. There's also high frequency energy associated with other motions not related to the tides. We want to get rid of these higher frequency subtidal or residual motions by running a filter at a particular cutoff frequency. So at 0.03 hertz, or about 33 hours, 0.03 cycles per hour, so 33 hours period, we're going to cut off all this stuff out here and then just look at the low frequency oscillations. And we do this with a nice time domain filter that Bob Beardsley developed from some people at Woods Hole, that Jim also clued me into and passed on to me. In any case, we're just filtering the data to get rid of things that have shorter periods than about 33 hours. Okay, so what you're left with then are the subtidal magnitudes and directions. So the upper panel, again, showing magnitude and directions in the lower panel. It's the same figure I showed you before, but now it's only the subtidal motions. The magnitudes change up to about 25 centimeters per second, and they vary significantly throughout the domain. There's also a very strong vertical structure, meaning that there are very strong currents at the surface compared to what's happening at the bottom. So the currents are attenuating with depth, varying over several days, not on the tidal cycle, and changing in direction also very strongly as a function of weather forcing on the inner shelf. So we want to look at this a little bit more closely. I'm not as interested in the vertical structure, meaning the ways we did this before with the tidal currents, but I want to look at the relationship of the surface currents, mid-depth, and the bottom currents relative to the wind fields. So we'll look at the near surface, mid-depth, and bottom, and plot that as a function of time, also with the wind patterns. In the upper panel here, this is the current and wind direction. The wind directions are shown in black, and this is now not the direction from which the wind is coming, it is the direction that the wind is blowing. So it is in the same direction that the currents. So if the winds are blowing towards the north and the currents are going towards the north, they're coherent, if I should say right. The bottom panel is the magnitude of the winds in black and the magnitude of the currents in the colors. So the green is data from the upper near surface water column. The blue is from the mid-depth, and the red is near the bottom. So what we find in directions is that the near surface, mid, and bottom currents offshore generally follow the wind patterns. That is to say, as the winds move around, so do the surface, mid, and near bottom currents. There is some vertical variation. There's rotation as you go down into the water column that we saw before. And there's also amplitude decay. If you have stronger currents near the surface than you have near the bed. So you get amplitude decay and you get rotation as you go down into the water column. But in general, offshore, the direction of the winds determines the direction of these subtidal currents. That doesn't always happen. Notice that we have a rapid passage of a system that went through, and we do not see any response to those subtidal currents. So there are also other things going on other than just wind forcing at this particular site.
How much the altitude of your bottom measurement there?
The magnitude?
So the altitude, what depth is that?
Oh, the green is the near surface, so that's right below the trough line. The blue is at the mid depth, about 4 meters water depth, and the red is at the near bottom, at this point about, I think, 1.7 meters above the bottom. Okay. And if you look at the magnitude, you can also see that the magnitude of the wind also is modulating the current structure. That is, the currents are responding to the magnitude of the winds. When the winds are stronger, the near surface currents are also stronger. You can see a fairly close relationship there. That doesn't, again, always happen, again, where we're not following the winds here. Again, the magnitudes are not behaving, so something is going on there we don't really understand at this point. And the same is true for the near, mid, and near bottom currents as well. So the winds offshore are clearly modulating the current response most of the time. Okay, and the magnitudes of those flows, again, are upwards of about 30 centimeters per second, 25 to 30 centimeters per second. Okay, well, let's look what happens once we get inside the inlet itself. So the first thing we'll look at is the ADCP in the main channel, which is in about 8 meters water depth. Okay, so once again, these are the currents, same figure that I showed before with magnitude at the surface and direction at the bottom. And the main thing to notice is that the magnitudes change most dramatically, other than on the tidal cycle, also during the occurrence of the spring tides, which had currents which were about almost twice as fast as they were during the neap tide periods. And the currents are almost 2 meters per second. So they're very strong currents inside the inlet itself. The phases, or the directions of the current, tend to be very ordered. They're either onshore or they're offshore. And those changes happen very rapidly. And I'm going to show you a close-up here again in the middle so you can see this a little bit clearer. Here are the magnitudes of the current, and here are the changes in directions of the currents that happen very rapidly. Also note that under the crest of the wave, this is where we have the strongest onshore currents, and the strongest offshore currents are occurring at low tide. The currents are actually slack tide for maybe a minute or two right at mid tide. So this is those progressive waves that we're seeing. They're not standing waves. I had not seen this before, but we needed to know this because when we deployed our instruments, we needed to know exactly when slack tide was, so we had to know this ahead of time. In any case, we have very strong variations in directions that are determined by the orientation of the bathymetric contours in the inlet. They're not free to go wherever they want. They're collimated and guided by the contours themselves. Okay, so once again, we can look at time series. We can filter these time series. These are the currents in the north-south and east-west directions. These are spectra, again, removing the tidal constituents. A couple of things to point out is that there are a bunch of constituents that are not removed because these are shallow water effects on the tides, other nonlinear effects, and other motions unpredicted by the tidal forcing mechanism. So there are additional residual forcing. We don't really care about those right now. We're going to filter this out again and only look at the low frequency fluctuations associated with the subtidal motions. So we can do the same thing again. We've got magnitude of the subtidal components, and we have direction of the subtidal components here. Notice that the directions are always, in a particular direction, they're always pretty much headed out of the inlet itself. Okay, you can ignore these periods where you have these real strong things here for two reasons. One, currents are very weak there, and you have to be careful with the last 3 days on either end of this filter. And so funny things happen at the end, and so these aren't really real in terms of this sudden change in the direction of the currents themselves. But again, there are magnitudes of these subtidal currents that are as high as 40 centimeters per second. And the changes in the currents tend to occur on much longer timescales than the tides. Several days, once again, we think this is driven by the weather force patterns. So again, we'll look at the surface, the mid, and lower water column, and compare these to the wind vectors that are driving the currents offshore in this area. So the upper panel again shows the directions that the wind is blowing, that's the black line, and the response of the currents here. These are the subtidal directions associated with the subtidal motions at the inner inlet position. And the lower panel shows the magnitudes of the flows. The first thing to notice is that the currents don't follow the wind directions. The subtidal components are also aligned with the bathymetric contours to a certain extent. Notice that the surface currents and the mid-depth and the bottom currents, there is some rotation associated with that. There's about a 30-degree rotation in the subtidal flows from the surface to the bottom. And most of that rotation typically occurs near the bottom, although that varies depending on where we are. Interestingly, the magnitudes of the currents, these are the green, red, and blue lines, are 180 degrees out of phase with the magnitudes of the winds. That is to say, when the winds are high, the currents tend to be weaker. And when the winds are weaker, the currents tend to be larger. We don't fully understand what exactly is happening here. But we know that there's a relationship between the winds and the subtidal currents because it's very clear. When the winds are low, the subtidal currents are high. When the winds are high, the subtidal currents are low. So there's about a 180 degrees or out of phase component associated with these fluctuations. Okay, so if we now look at the other side of the inlet, can't point there, got to point over here. So we have out of phase currents over here. So something's happening to the circulation associated with the subtidal currents that's inversely proportional to the winds. On this end, now we'll look at this is shallower over here, but we'll look at this ADCP. Notice that the mean depth is about 1.5 meters. This is relatively shallow. Again, we have modulations owing to the spring tides and so forth. We can conduct the same analysis and get to the subtidal magnitudes and directions. Despite this shallow depth, we still have subtidal currents on the order of about 20 centimeters per second. They tend to be very strongly vertically modulated, even over this 1 meter water depth. And they tend to be very strongly rotationally dependent, as the rotation is very strong in the shallow water. One thing we found with the tidal analysis that I did not discuss before is that rotation of currents in relatively shallow water can be very strong owing to the impacts of the boundary layer on the flow pattern. So it's not surprising to see the shallow flows in 1.5 meter water depths to be very strongly rotationally and amplitudinally modified. Once again, we can look at the near surface, mid, and bottom depths and compare these to the wind. And what we find is that, again, the currents, especially at the surface, don't really depend on the direction of the wind. They're once again dependent on the orientation of the shoreline on the northwest side of the inlet, northeast side of the inlet, and the direction of the currents themselves. Also note that the magnitudes of the currents now, which are much stronger at the surface and mid, we lost our scale over here. This is about 20 centimeters per second. Now we're in phase. That is to say, the subtidal currents on the northeast side of the inlet are now in phase with the wind forces, so that when the winds get stronger, so do the winds, and when the winds get weaker, so do the subtidal currents. There's also very strong amplitude decay over the water column and very strong rotations, as you can see from the directions. So there's a very complicated subtidal flow pattern in the north and south part of the inlets. Okay, final thing I want to talk about in terms of subtidal currents is we can just look at the monthly average mean flows. The tidal currents, by definition, are going to average to zero. We remove those using spectral techniques, which assumes a zero mean. So what we're left with is the average current over the entire 4-week period. This is offshore, this is inside the main channel, and that's on the northeast on the secondary channel in shallower water. So we have east-west currents on one axis and north-south currents on the other. And they're about 5 centimeters per second on average, going due east at the surface. But then they rotate as you go down into the water column. So these subtidal currents, these mean subtidal currents over monthly-long periods, rotate as you go down into the water column in a very organized manner. This is representative of boundary layer kinds of behavior. Also in the main inlet, now we've got mean subtidal currents exiting the inlet on average with about a 15 centimeter surface velocity. So these subtidal currents inside the inlet on the main channel are always headed offshore on average. And they're probably having something to do with the larger scale back bay multiple inlet system in the area. So there's something that's basically making this 180 degree, the fluctuations in that subtidal flow are probably due to something happening on the larger scale. Also note that there's more or less uniform to the upper 2/3 of the water, or the upper 2/3 of the water column, and there's a sharp rotational change as you get down towards the bottom. So there's an amplitude decay and about a 30 degree rotation as you go down into the water column. On the north side of the inlet, northeast side, now we have about 5 centimeter per second currents. And these currents are now headed in the direction onshore, aligned with the bathymetric contours. So now it looks like we've got mean subtidal flows headed out the inlet and other subtidal flows heading in the inlet on the other side. So there's a circulation pattern and a gradient associated with these subtidal flows. So those gradients can lead to things like deposition and erosional patterns, depending on the nature of the flow fields associated with those gradients. So what we think is happening, at least on the large scale, is that flows in the north side of the inlet, on average the subtidal, are headed up the inlet, and subtidal flows are headed out the inlet here, and on the shelf, they're headed in that direction. So there's this general circulation associated with the subtidal currents in the inlet itself, and may have something to do with the depositional patterns associated with this central shoal that tends to move around a bunch within the inlet itself. In fact, they're doing a lot of dredging in the area because of the behavior of this inlet. It may have a lot to do, not so much with the tidal flows, but with the lower frequency oscillations in the flow field associated with the subtidal motions. Okay, so New River once again has a very narrow, shallow, tidally choked inlet system where the tidal currents are actually attenuated greatly by the time we get to the back bay. It looks like progressive waves just as soon as you get across this ebb tidal shoal, and we're looking at orbital velocities with the crests and troughs of those waves. And we also see that there's a complicated subtidal flow pattern within the inlet itself that probably has something to do with the larger scale back bay system, particularly at the effluent associated with the outgoing ebb tides. Okay, so let's just summarize real quick so we don't lose ourselves before the end, and that is that a New River outside the inlet, tides are standing against the coast, but inside they're progressive. This is basically the tidal choking I was talking about. For example, at Hampton Inlet, they're standing pretty much everywhere. At high tide, you can pretty much count on roughly that that's going to be slack tide. Subtidal currents outside the inlet generally follow the wind patterns, also the case for Hampton, which we did not discuss. Inside the inlet, they're both out of phase and in phase with the magnitudes of the wind. And they form a horizontal circulation pattern that may have something to do with the sedimentation within the inlet itself. Okay, so those are sort of the take-home messages that we have related to these subtidal currents within the inlet itself. Okay, I want to now move on to looking a little bit more at that forcing mechanism. And to do that, we're going to come back to the New England area. This is, again, a Google Earth map. I'm sure you all recognize it. This is Portsmouth over here with Portsmouth Inlet at the Piscataqua, heading up into the Little Bay and up into the Great Bay. Here's the Isle of Shoals with its Seaman station on it. And down here is Hampton Inlet. So I want to talk about data that was, first I'll compare barometric pressure data between these two stations. We're interested in knowing what the large scale pressure fluctuations are because we want to correct our pressure gauges with atmospheric pressure, those that need it. And so we need to make sure that the scales over which we're looking at can actually be done appropriately. We also have Fort Point tidal data here, which we'll use to measure the subtidal components in the water level fluctuations and compare those to data up in the Great Bay. This is 25 kilometers of river up to Adams Point in Ferber Strait, and another 5 kilometers up to the Squamscott Railroad Bridge. It's also about 12 kilometers to the Isles of Shoals, and about 16 kilometers again to Hampton, and between here it's about 25 kilometers between Hampton and Portsmouth. I also want to compare what's happening at Fort Point with what's happening outside the inlet at Hampton, and also what's happening inside the inlet at Hampton. So I'll talk about the individual data sources in just a moment. First thing to compare, though, is the barometric pressure, basically seeing what the patterns look like between these two stations. This is the atmospheric pressure head fluctuations as a function of time in 2011. So this is about a little over a month, about 5-week period. And the red line is the Seabrook Met Station, the blue line is the Isle of Shoals. We can actually measure quite well what those atmospheric pressure fluctuations are, and we can use those to correct for any pressure sensors that we may need to in the vicinity. We feel very confident about that. Maybe that's not a big surprise to some of you, particularly you atmospheric scientists. In any case, we want to do that. Okay, the next thing I want to do is compare subtidal fluctuations in the pressure fields or the water level here at Fort Point with what's going on at the Squamscott Railroad Bridge up here. This data was collected in 2010 by Jim Irish and Sean Denny, and this is a radar station. It is, has no atmospheric pressure fluctuations that need to be corrected for. So it's an ideal sensor to basically to make these comparisons. So the question is, are things that are going on out here, are they driving what's happening up in here? Or is it local effects of winds blowing on the Great Bay that's driving the fluctuations? So one way to look at that is to compare the subtidal amplitudes. Red is Fort Point and blue is at the Squamscott Bridge, to see whether the magnitudes vary in time. And you can see that the agreement is quite good, that the magnitudes of the subtidal water level fluctuations at the Squamscott Bridge virtually follow precisely what's happening down at Fort Point, suggesting that the forcing mechanism for what's happening at the Squamscott Bridge is not happening in the Great Bay. It's happening offshore on the continental shelf, where the weather force patterns are driving pressure gradients at the mouth of the inlet. We can also make comparisons at the Jackson Lab. This is a bubbler wave gauge, which has a differential pressure system that also does not need to be atmospheric pressure corrected. And you can see that the fluctuations don't precisely follow the magnitudes of the currents, probably are magnitude of the subtidal amplitudes, probably owing to potential differences in the way that the sensors make their measurement, that is errors, and also funny things that may be happening right at Ferber Strait, where you have a lot of nonlinearities associated with large instabilities, where you have big gradients in the flow patterns. In any case, this is very typical of some of the data we've seen, where the data follows significantly closely for a while, and then it deviates a little bit. Even though the magnitudes stay the same, there's offsets between those, which may be due to the sensors themselves. Okay, so what we find is that the fluctuations in the subtidal amplitudes at Fort Point are driving what's happening up here in the Great Bay, particularly to first order. We can also compare then what's happening between the subtidal amplitudes here and 25 kilometers down the coast to what's happening in Hampton Inlet. So let's look a little bit closer at Hampton Inlet so you can see the array of instrumentation that we have here. These are ADCPs that we deployed in 12, 7.5, and 1.5 meter water depths in 2011. And then there are a bunch of tidal gauges that were deployed by Jim and Larry Ward in 2005. And we'll look at some of those data. The nice thing about those is they're within the inlet itself. In the 2011, we really don't have anything back in the harbor itself. We would really like to know what's happening in there as well, so we'll use the 2005 data. But first, we'll make some comparisons along some of these ADCP data, which have pressure sensors. So this is the Fort Point data in red against the 12-meter offshore ADCP at Hampton. And what you see is that the fluctuations match very well, particularly for being away by 25 kilometers. The differences here are less typically than a centimeter. What's happening at the ends, you have to be careful about the filtering. that the deviations in the ends within a few days of the ends are probably separating things, and we can't really say anything about that. So you really have to ignore what's happening at the end of the records owing to the effects of the filter on the data itself. But for the most part, the data follow very closely what's happening at Ford Point and what's happening on the shelf near the shore in Hampton. You can look again in 7-meter water depths, and again the agreement is quite good except for the ends where we have filter effects that we're a little questionable about what we can talk about there. But nonetheless, the agreement is quite well. So the fluctuations in the subtidal amplitudes at Ford Point and Hampton are very strongly correlated. If you move inside the inlet again, we see a similar kind of thing that's going on. This sensor here had to be removed and put back in every week. And that's where these gaps here are all about. And it looks like after time that there's some kind of a drift pattern, probably associated with the pressure sensor. Either the sensor is sinking into the sand, the pipe may be sinking, there was a lot of change to the bathymetry in that area, the sensor may be moving in time. So there's drift patterns associated with where the instruments are that may be leading to some of these deviations. We don't think these are real sort of subtidal fluctuations that are not driven by the shelf motions. And one reason we think that is because we can compare data, again, from Ford Point with some of these data back inside the inlet itself made in 2005. We'll start with Seabrook and look at some of the other piers at the Yankee Food Co-op, Chenard's, and at Normando. So these are now 2005 data ranging about 5 months collected within the inlet at Seabrook. And you can see that the subtidal amplitudes pretty much within the inlet follow what's happening at Ford Point the entire time. Talking to Jim and Larry about these data, they really have good confidence in the Seabrook tide gauge, so they really like what it's doing, and there's no real drifts, and we get very good agreement. So once again, the railroad bridge at Squamscott, offshore at Hampton, and again at this sensor we get subtidal fluctuations that match between Ford Point and that location 25 kilometers away very well. Some of the other sensors have a little, oh, I should point out one thing. I meant to do this right here. Big fluctuation at Ford Point, no response back here at Seabrook. So this could have been something happening at the gauge at one of the two locations. Could have happened at Ford Point, we don't really know. But what we do know is that same fluctuation is not recorded at any of the other sensors within Hampton. So either there's something that went on with the gauge at Ford Point at that time, or there's subtidal motions that could be occurring to local processes, which we saw at New River, that could be happening as well at Hampton. That would be expected as well. So anyway, this is the data at the Yankee Fish Co-op. Once again, the fluctuations match. There appears to be some drift associated with it, probably owing to the sensors. Similar kinds of behavior at Chenard's Pier. The fluctuations match. Looks like there's a trend, probably something shifting in the sensor itself at that point. When it was redeployed, there are basically no shifts in the data. So once again, one more, Normando's Pier on the other side. We're not seeing that fluctuation on that side of the inlet as well. There's no real changes across the inlet itself. We're still being driven by things on the continental shelf. Okay, final thing. I want to go back to the currents. So the currents up in the Little Bay and Great Bay, some other people have been looking at nutrient fluxes owing to bed shear stress. I don't know if Megan's here or not. She did some field work as part of her master's degree with Linda and Diana and myself up here in the Little Bay and Great Bay area, and found that during wind events there was enhanced shear stress near the bottom. She attributed this to the enhanced flow field owing to the winds on the water. And I immediately said, well, wait a minute, Jim's been telling me about the stuff that's driven not by what's happening on the Great Bay, but what's happening out here on the shelf. And we saw that with the amplitudes in the pressure, but what about the currents? So what we're going to do is look at currents here in Ferber Strait. These are data collected in 2007 by Carl Kammerer, and also currents here. I'm not going to show those, but there's currents here in a number of different instances along the inlet itself. But we're just going to focus on what's happening right here at Ferber Strait with an ADCP deployed there. This is the data in 2007, and it lasts about 5 weeks. Again, these are the tidal fluctuations. You can see the changes in the current directions happening on those semi-diurnal timescales. And these data are not exactly turning around, they're not exactly looking like standing waves. They're mostly, but there is a slight phase shift owing to the amplitude changes as you move up the inlet. It's partially tidally choked. That is, there's amplitude changes in the tides as you move up the inlet. Nonetheless, that's a separate story. We could again do the same analysis we did before, remove the tides and look at the subtidal forcing, and this is what we see. The upper panel is the magnitudes and the lower panel is the directions. So the magnitudes vary again on longer time scales than the tides, and they show very strong vertical variation, dropping from anywhere from 3 to 4 centimeters per second down to 1 or not. And the rotations are very strong over the water column. There's very complex subtidal patterns. But one thing to note is that the subtidal currents here are not very big. They're only 4 to 5 centimeters per second at their largest. Typically, they're only a couple centimeters per second. The subtidal forcing from these large amplitude subtidal currents are not very big. And that's partially due to the fact that the depth, we think that the depth in the inlet itself in the Piscataqua is quite large, 25 meters at the mouth and 25 meters at various places along the transit as you come up the Piscataqua into the Great Bay area. So it's very deep, there's a lot of flow coming in, and the magnitudes are correspondingly of the currents smaller. You're moving a lot of flow, you can't move it that fast, particularly at the subtidal periods. In any case, we can look at the structure of that flow, and I was going to show a simulation, but I didn't quite get to it. So you're only going to see a snapshot. This is all the currents. These are the residual high-frequency currents not related to the tides. And these are the subtidal currents at a particular time. So the subtidal currents, you can see this rotation as you move up into the water column. It's very coherent. You can watch the slowly varying and do these really interesting things with the currents that are clearly being impacted by what's happening at the bottom. There's a boundary layer influence to what's happening. The other thing to note is that these residual currents, in this case, are very strong relative to the currents in the subtidal. At this particular time, the magnitude of the tidal currents are about 75 centimeters per second. The magnitudes of the subtidal currents are about 10 centimeters per second. And the magnitudes of the subtidal currents are again about 1 or 2 centimeters per second. And the magnitudes of these high frequency nonlinear affected currents are sometimes stronger than the tides, particularly as you get to low tides. And that's due to the interactions with the bathymetry, nonlinear effects with the current bottom interactions, but also nonlinear shallow water tides are coming into play. So there's a lot of eddies and things. If anybody's been around Adams Point, you know that there's a lot of eddies and things around there. It's very complex. And that spatial variability in the current creates these high frequency motions. In any case, the subtidal currents are not that strong. So it's not clear to me anymore whether or not it's the subtidal currents that were leading to Megan's observations of enhanced shear stress there. It may be due to other factors as well. Yeah.
So what is the direction on the residual and the subtidal currents in the surface and the bottom?
Can't you tell by all this mess? These are the north-south currents here, and these are the east-west currents here. So this is basically headed to the north and to the east. So this is basically, actually it's mostly to the north, it's almost entirely to the north. So this is headed north. So this is an ebb tide. At Jackson Lab, ebb tides go due north.
But that's averaged over the 5 weeks, correct?
No, this is one 30-minute average. This is one 30-minute. It's a 30-minute average. So this is just one snapshot in time. And you can watch these through the simulation.
So that's not the 5 weeks?
No, this is one 30-minute average up here on a particular day. I can show you the simulation that you can watch the currents evolve in time. It's kind of cool. So if anybody's really interested, I'll show it to you sometime. Okay. So conclusions. The barometric pressure fluctuations at the Isle of Shoals are strongly correlated with Hampton, which means we can correct for our pressure gauges as needed in the area without worrying about it. The subtidal water elevations in the Great Bay closely follow those at the mouth of the Piscataqua. That's 25 to 30 kilometers downstream of those observations. The subtidal water elevations also on the inner shelf and within Hampton Inlet also follow closely what's happening at Fort Point. So these two observations suggest that we have large-scale forcing patterns on the shelf that are driving the subtidal flows up in the inlets themselves. And this happens over a relatively large scale. What's happening at Hampton is pretty much what's happening at the Piscataqua. So the scales of the weather forcing are large and not local. Subtidal flows at River Strait have strong vertical structure, but they're relatively weak compared to shelf currents of either Hampton and New River, but probably due to the magnitude or just the volume of fluid that's moving into the region because of the overall water depth. You can't move 25 meters of subtidal flow over 500 meter wide area. You just can't move it that fast. So the volume of the flow may be the same, but the magnitude of the current are less. Okay, and I want to summarize then what we know at New River. This is a narrow inlet with a very shallow ebb tidal shoal with lots of breaking that's going on over here. So a lot of wave breaking here. It's very narrow. So at low tide, there's only about 1 meter water depth. And at high tide, there's only about 3 meter water depths. So there's very narrow water, basically, that the waves can get in. The amplitude of the tides decay 90% by the time they get to the back bay. It looks like a progressive wave at the mouth of the inlet.
Well, does it really extend all the way up to the top of your picture there?
Yep, the tides go all the way here. By the time they're into the back bay, I don't know exactly where, but I think it's like 90% of the tidal amplitude is decayed by the time it gets to the first bay. So there's very little reflection coming back out. It's all orbital velocities happening down here.
So it's highly dissipated in that.
It's very dissipated, yes. It's very dissipated through there. So if you compare that to the Piscataqua, where you saw, 33% change in amplitude, it's not nearly as much as the 90% they have here.
That has a really small tidal line,
It's 1 meter at neap tides and 2 at spring. So it's like 1 to 2 meters. So it's a little less than it is here, but at spring tides, it's about the same as our neap tides up here. The inlet flows from the subtidal components are about 1 to 40 centimeters per second. And they show a complex circulation on average, but also an in-phase, out-of-phase component that suggests a complex circulation relative to the weather forcing that's going on, probably having something to do with what's happening back in here. Okay. In the Portsmouth and Great Bay estuary, what's happening in the subtidal magnitudes up in the Great Bay are being driven by larger scale processes on the shelf itself. Note that the inlet here is deep, 25 meters. There's no wave breaking really occurring on any ebb tidal shoal out here. There's certainly sand moving around, but there's not a lot of wave breaking there. There's changes in the depth, but in general, it's a large, deep inlet relative to New River. There's some decay in the amplitude of the tides as you get up into the Little Bay, about 30%, but not nearly as much as it is in New River. The currents of the subtidal currents are much weaker up here, probably due to the magnitude of the flow that has to come into there. That is, the volume of the flow is so large, you probably can't push that much water around so quickly. But it's significantly less than typically residual tidal currents, and in particular around the River Strait area are very determined by eddies and other nonlinearities. And finally, in Hampton, again, we have a narrow inlet. It's down here, narrow inlet with a smaller back bay. It's relatively deep compared to New River. It's like 3 to 5 meters water depth typically. So it's a little bit deeper. There is some breaking on the flanks, but not generally in the inlet itself, except during very large storms. And there's a relatively small back bay that's relatively shallow. So it has a little bit different behavior. So we have 3 different inlets depending on the water depth in the inlet itself and the size of the back bay. Subtidal currents here are as high as 40 centimeters per second, and they vary with the winds. I really didn't talk too much about that. We would like to get more data on the currents inside the inlet itself. We have pressure data, but not wind data. And once again, what's happening here at the mouth of Hampton is really being driven by large-scale processes that extend at least up into the Piscataqua. So relatively large-scale weather patterns are driving pressure gradients at the mouth of the inlet that are forcing the subtidal flows. Okay, that's it. Thank you for listening. I'm happy to take
Tom,
Yep.
I was just curious, in the New River, the deeper of the 2 channels that you were looking at, is there any evidence of like dredging or anything like that there?
As a matter of fact, there is. This channel right here, so there's a little bit of a story behind this. We didn't really want to go to this inlet because of complications of having a military base there, but that was the reasons why they asked us to go there. So they kind of dictated when we could go, and they moved our experiment. When they moved it the second time, it turned out the Army Corps was in the process of dredging the inlet, which from a scientific perspective is not a great thing. We don't really want to study a natural inlet when there's dredging going on. And so they were dredging this channel right here, and you can see evidence of it here. Right before we got there, and they said, well, we'll stop, you know, before we start. So there was a little bit of dredging that had gone on just as we got there. But they do a lot of dredging here. It's very shallow. Wave-driven processes and sediment transport is huge in this area. And this inlet is changing dramatically. It's very difficult to keep the channel open. The mariners there know exactly where to go and when to go. They don't need us to tell them how big the subtidal currents are to find out how to get in and out of the inlet. And they're pretty good at it. They don't come in at low tide. But when they come in at high tide, there's a lot of boats coming through. And the Army Corps has to keep that channel open. For some reason, they want this channel open. They don't want that one open. I can't remember what the motivation was, but there are currents. Some boaters come in on either side. We tended to focus what we were doing on this side of the inlet.
Was there did you average over the 5-week period in the Great Bay in Carl's data?
I have not looked at that yet.
Just
No.
wonder if there's a residual flow, like a net 2-layer circulation you might find in some estuaries.
I would not be surprised. If there's any freshwater input, there's got to be something going out or it would fill up.
That'd be
So,
interesting.
yeah, I should do that. I can do that.
On the topic of dredging, does this study, can it help you maybe optimize how they could approach the dredging, maybe in a way so that it would stay clear longer based on better understanding the processes?
Absolutely. Much of the research that we do is to try to understand what happens to the sediment transport in response to waves and wave-driven currents. Tides now are becoming a bigger deal. Subtidal currents, which were not included before, which we now think are important. So it's very complicated. There's people who work on the small scale boundary layer physics associated with sediment transport. And then we put together these numerical models to try to make these predictions. And we have people right now that are going to start doing this. That's one of the things that Salmi's going to do, is look at a numerical model to predict what happens to the flow patterns and what the shear stresses are, and then create a sediment transport. And we have people who have created models that predict sediment transport. Then they can start doing scenarios. All right, we're going to dredge here. How's that going to change? What would happen if we did this? What's the long-term behavior? That's a big part of nearshore processes research, which for a long time was focused on sandy open coast beaches. And now our models are good enough, very good, that they can start doing things in the inlet. Interesting thing about the modeling is that one of our modelers was trying to predict this tidal flow in the inlet, which is very strong and very large, and he thought it would be no problem. He could not predict the flows in this inlet unless he had good bathymetry up here. In fact, he was using old bathymetry and he could not make it work here because he had poor bathymetry here. He had to go back to the field, resurvey this himself in order to run a tidal model to predict the currents here, and then he got very good results. So there's clearly connections to remote bathymetry to any type of modeling exercise. So anything that NOAA or any other activities that we have in terms of mapping, the consequences of that mapping can be felt not just locally, but remotely, particularly for people interested in modeling what those currents are. You know, Carl's, making all the measurements, and there are people who use those to try to tune their models. By the way, models don't work with beads if we don't have any data typically. Our nearshore models are good, but unless you have data to verify those, they typically don't work. And tidal models, although we know the forcing really well, the currents are so poorly predicted that until you get some guidance, it's hard to even know if your model's working. So tidal currents are hard, and this is just killer if you have to know the bathymetry over here to predict it over there. That's killer. I was very surprised, and so were they.
Did you have any storm surges during your studies?
Small. The barometric pressure changes were weak enough that we didn't really have major changes. There were subtidal amplitudes, probably on the, we didn't actually measure those, but they were on the order of 10 to 20 centimeters, I would say. So typically those fronts that passed through didn't have huge surges associated with them. Just after we left, however, major hurricane area right here. Wilmington is real close, right down here. So they have giant surges that occur here that create huge problems to maintaining the inlets in the area. So during our experiment, we did not experience any of those major events.
Do you think looking at variations in the time delay between the tidal signal at Squamscott and Fort Point, or maybe River Trace and Fort Point, would tell you anything interesting about what's going on there and the forcing between the two?
Certainly with the tides, and that's something that Jim has been looking at ever since Carl's data came along. He's looked at the phase changes and the amplitude changes as the tides move up the inlet. So people know about those phase changes because the tidal charts and so forth know that high tide is a couple hours later. So there's a general understanding of that behavior, and certainly within the tidal model itself that can be done. In terms of the subtidal flows, I haven't really looked at that at all in terms of how those amplitudes may change or how the current structure may change as you move up the inlet. It may be very dependent on the geometry of the basin itself.
I have another question. I was thinking about your data sets and wondering what value there would be to a time-lapse camera from the surface of all of this. If you would be able to pick out from imagery from the surface currents and flows, eddies that are persistent over a long enough period of time, that would give you some better intuition from your point measurements at various places, if that would give any
I have a little experience measuring surface flows with video cameras in sort of a semi-previous life, not that long ago. And that's difficult where you don't have a lot of surface tracers. So that's hard from an imaging perspective. Yuri, I don't know if he's here, is really, really good at imaging stuff, might be able to help in that regard. Radar measurements tend to be very good for those measurements, but they tend to work on much larger scales. So it's a very difficult thing to measure is what's happening at the surface. We use our wave runner to measure currents, but we have to average those in time over a given length of time. So that's, again, very difficult to do, to quantify those spatial variability of the eddies. It's a very difficult thing to do. Arrays of instrumentation is probably the best thing that you can do. You can put out known arrays as a function of the larger scale mean flow patterns, that is the incoming and outgoing tides, and do array analysis to determine what the magnitudes of those currents are. And there are ways to sort of determine whether those are eddies that are being swept along by the currents, which are nonlinear processes, or whether they're tied to the fluctuations of the current themselves. So fixed instrumentation, because you get good time resolution, is probably the best way to do it. But you would need an array of those strategically placed. A spectacularly fun experiment to do. If anybody's interested in Jim, if you could get some more instruments, we could do it. But
all we need is money.
That's all we need is money, that's right. Anyway, so there are really cool things to be done, both in Hampton Inlet, incidentally, where we have measurements, where there's also really strong flows, which are very narrowly constrained in the inlet. So you get gradients, lateral gradients, that drive enormous instabilities. And there are theories to predict exactly what those are. It would be a spectacular place to work and do exactly that. But I don't think I would do it with cameras, or unless there's another way of measuring the surface currents reliably in fine enough scale. Maybe infrared or microwave stuff. I honestly don't know. Tracers, they use tracers a lot. In fact, at New River, they did a lot of experience with what happens to the flow. And they put dye in, and the dye would go out, and then some of the dye would come back. And then it would go out again, and they would watch this and would look at it from the air. Well, it was super cool. I just can't help but tell you about this stuff. Where's the New River? Is this New River? Yeah, New River. So they would put it in different places. Some of it went down the coast 50 miles down the coast and just hugged the shoreline. So when you think about putting something in the water, effluent from something here, I'm not even going to mention what that might be, is it going to go and impact things far away, close to shore, or is it just going to go offshore and mix? It just hugs the coast. Putting up and closing this beach here because something happened up there will do nothing to what's happening down here. So the transport we're finding based on flow in and out of this inlet is very complex, and it tends to be very tightly coupled to the nearshore processes. And this we're finding out in a lot of different areas. And in fact, even in Hampton, I'm sure there are things that are going on that are very tightly coupled to the inlet and the beach processes there.
Well, I'm sure Tom can answer any other questions a little bit after. We
You
won't
can
hold
go.
anybody too long. But thank him one more time, please.
Yeah. Thank you.